Okay, so we are picking up where we left off. Oh, so I wrote myself a message here to review the orbital diagram. And so since I wrote this for myself, I'm going to go over and look at what, okay, so when we met on Monday, we're talking about how to figure out the number of electrons, electronic configurations. So before I continue from here, I want to make some amendments to the 4 quantum numbers for carbon. So this doesn't just apply to carbon, it applies to carbon, nitrogen, oxygen, and fluorine isn't really affected. So I want to go over that. But before I go over that, I have to talk about the orbital diagram because the changes I'm going to be making make sense after we cover the orbital diagram and then we cover Hund's rule. Okay, so based on how this book is written, we're covering the orbital diagram and Hund's rule in a different chapter than we cover the quantum numbers. So all of these changes I was discussing on Monday and today are due to having many electrons within the atom. Okay, so we talked about the energy levels and the sublevels and the order in which they fill. S will always be the lowest, P, D, and then F. But we talked about the ability for a sublevel to penetrate. And when we see that happening, that's when we have, instead of having the sublevels fill in the order S, P, D, F, the orders kind of distort for a little bit because of those ability for the sublevels to penetrate. And then you have the 4S sublevel filling before the 3D sublevel. Okay. So after seeing all that, we talked about the term degenerate. We're told here when orbitals are in the same sublevel, they have the same energy and they're called degenerate. So what they mean here is, for example, let me give you guys examples of degenerate orbitals because all of this eventually helps us to talk about Hund's rule. So example of degenerate orbitals. Okay, see my spelling is off here, degenerate. Yeah, orbitals. So S only has one orbital in the sublevel. Okay, so I'm going to write here the energy level. And then I'm going to write here the sublevel and therefore the orbital. So let me write this a little bit to the left. So I'm trying to kind of make this up as I go. So I'm trying to figure out how I want it to look. Energy level. Oh, my spelling this morning. Sublevel. And then the orbitals. Okay. So I'll start with energy level 1. Energy level 1 only has one S. With one S, we only have one orbital, right? With energy level 2, we mentioned this last week. We're mentioning it again this week twice. With energy level 2, we have 2S, and the 2S always has just one, the S orbital always has just one sublevel, right? And then one orbital. So when you're looking at 2S, let me actually write this vertical, it'll be a lot easier for me. 2S, this still has one orbital. But when it comes to 2p, 2p is part of 2s because you see they're all in energy level 2. 2p actually has 3 orbitals. We talked about this before. It will have the px, py, pz. So when it comes to this level here, when we're talking about the orbital diagram, I'm going to show you a box to represent the orbital diagram. So the more I talk, the more I realize I should have made this a little bit, added more room. But since I'm going to be working on it some more, I'll be fine. Okay. So the orbitals that are on the same sublevel, these are called degenerate. So I'll put in DEG next to it. Degenerate just means that they're on the same sublevel, the same level of energy. Okay. Then for energy level 3, we have 3S. This is everything here, 3P, and then we have 3D. And for this, once again, anything that's S, we only have one orbital. For the P's, we have 3 orbitals. For the D's, we have 5 orbitals, right? The ones that have more than one, the orbitals tend to be degenerate. Now, when you get to upper level chemistry, you will see how the D sublevel, the one with the 5 orbitals, it's able to actually split. But at this level here, we're keeping it simple, right? As we're learning things and we go into deeper chemistry stuff, we tend to modify what we learned before. That's just how chemistry is unpacked, okay? And then we have energy level 4. For energy level 4 here, let's see, energy level 4. I'll just end with that one. We have 4s, we have 4p, we have 4d, and we have 4f. So for this, remember, s's we always have one orbital, p's we always have 3, d's we have 5, and then f we have 7. So remember, the ones that have multiple orbitals in the same sublevel, the way I visually see this is like having a shelf, right? Here you have a shelf and you only have one item, which is one orbital on the shelf. Here you have a shelf and then you have 3. And the 3 orbitals are essentially the 3 items on that shelf. Here, you of course, you have 5. And we'll go through and draw that later on in context. So these are degenerate because they have to be at the same level. These are degenerate. These are also degenerate. Okay? We're learning the beginning right now, so we're keeping it simple. I'm bringing this up because some of you may go online and you may learn things we're going to be learning later on, but this is the order right now. So 3 degenerate orbitals, 5 degenerate orbitals, 7 degenerate orbitals. Remember, degenerate just means they're at the same energy level. Okay? So as long as the orbitals are on the same sublevel, they have the same energy level. And they gave you the example there, and I went through and illustrated extra ones. Okay. So we talked about Pauli's exclusion principle before when we're talking about how many electrons can be in the orbital. We're told here, according to Pauli's exclusion principle, in order for 2 electrons to share the same orbital, to be orbital mates, their n, their l, the m sub l values must be the same. But Pauli's rules has exclusions, right? Where it says that for electrons to be orbital mates, he doesn't use the term orbital mates, but to share the same orbital, they have to have an opposite spin. So this is showing you the opposite spin. These are 2 electrons in the same orbital. They have opposite spin. Same thing over here. These electrons do not have opposite spins because they're technically in different orbitals, right? These are the 3 different orbitals we see in the p sublevel. Okay. So what else do we see as a property in the filling of the electrons in the sublevel because the element has many electrons? So we are looking at electronic configuration for multi-electron atoms. So while we are here, I want to go ahead and review the quantum numbers. So here's where I'm going to make some modifications, okay, for the quantum numbers. So I'm going to start with, I'm looking at my periodic table here. I will start with, I'll just talk about the set of carbon, nitrogen, oxygen, fluorine. Okay, so before we talk about that, let me erase these notes for myself. The orbital diagram is the picture representation that shows you how the electrons are placed in the sublevel. This gives us more information. So you can see here, I have the orbital diagram, right? So the orbital diagram, as you can see, is a diagram that uses boxes to show orbitals. Okay, so you're seeing the boxes that show or represent orbitals and illustrates the distribution of electrons. So since we're looking at electronic configurations, I want us to go back once again and look at the 4 quantum numbers. But before I do that, we have to at least see how the orbital diagram plays out. So we have an example here with carbon. So let me start with carbon. And I feel like it's easier to draw the orbital diagram once you have the configuration, okay? So remember, starting with carbon, carbon is an element that has 6 electrons. So I have my periodic table right here. Carbon has 6 electrons, right? We're going to place all 6 electrons. Now remember, oh, I remember now. I had the sub-level periodic table. I think it was somewhere on the top, and I copied one to put it down here. Oh, there it is. because it's hard for me to keep scrolling back and finding this. We're trying to place the electrons in the element carbon. So remember, all first electrons go where hydrogen is. So this is the first electron, second electron. Now remember that even though helium is on the right, for this purpose, I'll move it left. It's okay to do that. 1, 2, 3, 4, 5, 6, right? So we're trying to place all 6 electrons from carbon in their respective sublevels. You can see 2 electrons go in the 1s sublevel. 2 electron 3 and 4 go in the 2s sublevel. Then the remaining 2, even though the 2p sublevel has the capacity that goes up to 6, we only place the remaining 2 electrons, electron number 5 and 6 in the 2p sublevel. Okay? So that's what I'm going to write here. Where was I? Back here. Okay, so when I get to the 1s sublevel, I'll place 2 electrons, right? In the 2s sublevel, I'll place 2 electrons. In the 2p sublevel, even though the capacity is 6, I'll only place 2 electrons, right? This is my electronic configuration for carbon. So right here, EC for electronic configuration. Now, I told you what the orbital diagram does, right? So what I like to do, I like to connect these things because that's how I remember. I told you guys earlier, each S sublevel has 1 orbital, right? We did all the work up here to illustrate that. So for each orbital, I'm drawing a box. So here, I'm going to draw 1 box for the 1s orbital. Now, the way they do it in the book, they don't put in the number of electrons up here. I like to do that just because it helps me when I'm doing my work. It helps me confirm what I'm doing up here. So I'll leave the configuration on the bottom. So for each S, I draw a box because each S sublevel has got 1 orbital. Each P sublevel has 3 orbitals, right? We went over that already. So 3 orbitals, that's 3 boxes. Let me see if I can draw all 3. 1, 2, there's the third. Okay, so now we're coming into the science is called Hund. Hund's rule explains the filling of the electron in the sublevels. Now, he says when you're filling orbitals that have the same energy, in other words, the degenerate orbitals, place 1 electron in each orbital before completing pairs. In other words, and when I was learning this in school, it made more sense because I had lived in a dorm. And the way they put people in dorms when I was in school is sometimes they wanted a person to at least occupy a room so the room can be cared for. So they'll put 1 student per room. And then when we got more students, like, hey, you got a roommate. And I'm like, yay. I didn't like sharing the room. I preferred to have my own room, right? So I can have things exactly the way I wanted them. So when we had more students, like, yay, more students. And you're like, okay, they're going to be your roommate. Yay. Okay. So when you have the sublevels, the degenerate sublevels, like in the P sublevels, you want to place 1 electron in each orbital on the sublevel before you go back and pair. So once each orbital is occupied by 1 electron, then you go back and start giving each electron an orbital mate, aka roommate. Okay. And we can say that applies here, but as you can see, you place 1 electron first and second one gets placed there. It's hard to really see that play out in the S sublevel. You see it in the P, the D, and the F. Okay, so I'm going to show you that here. First electron goes up. Now the order here, remember electrons are shown as arrows, right? The order here is the first electron comes in first, and the first electron usually upspin, second electron downspin. So in a way, I'm obeying Hund's rule. First electron upspin, second electron downspin. Okay, well now we have 2 electrons. First electron upspin, second electron doesn't come in here. The second electron actually goes here. Okay, if you have a third electron, that will go right here. So remember when I was telling you guys about the quantum number, the 4 quantum numbers? Yeah. We have to modify the quantum numbers, not just for carbon, but for carbon, for nitrogen, and for oxygen because of Hund's rule. And we are learning Hund's rule after the fact. So what I mean by that is, Let's go back to the periodic table and see how we would have assigned the quantum number. It would just affect the last quantum number, the m sub s. So right here, the 4 quantum numbers for carbon without considering Hund's rule. Okay, if you don't look at Hund's rule, this is how you will write it. This is how I taught you guys before, because this is how I learned it in this order. If you don't look at Hund's rule, then you will go back and look at the 4 quantum numbers here in the periodic table. Why am I getting a lot of email? Okay, guys, give me just a second, because I feel like somebody just emailed me from your class. Give me just a moment. Okay, I'll address that one later. Okay, so we're right here. Let's see. Carbon. So remember, from the 4 quantum numbers, we said for the N, L, M sub L, M sub S, energy level for carbon, this is 1, this is 2. So we'll say it's 2, right? L is 0 here, L is 1, L is 2, L is 3. So we'll say, oh, I wrote in the way. For this one here, L is 0, right? Oh, L is 1, sorry. So for, I wrote this in the wrong place. This is L is 1, this is L is 2. By rewriting this, now I've kind of messed up. Yeah, L is 0, L is 1, L is 2, L is 3, right? So for carbon, L is 1, right? For the M sub L, we accurately said, I need this space here. The M sub L, this is -1. This is positive, this is 0, this is +1, right? -1, 0, +1. So the M sub L for carbon is -1. Now the issue comes in when you're dealing with the magnetic spin. If you use the periodic table alone and don't consider Hund's rule, then carbon ends up having a magnetic spin of -1/2, right? Because boron will have the positive electron up, the negative electron will come in from carbon. But because Hund's rule actually modifies that understanding, as time went by, scientists realized, oh no, the electrons don't pair. When they have the sublevel, the electrons don't pair until each of the orbitals in the sublevel is full. So what I mean by that, remember the p sublevel essentially has 3 orbitals, like that, and like that. So by looking at the periodic table alone, even though it shows that boron and carbon are roommates, in reality, the 5th electron goes here, the 6th goes here, the 7th goes here, then the 8th goes here, the 9th goes here, and the 10th goes here. In the end, the final picture looks the same, but the process of filling is different. Okay, so please notice that. So because of Hund's rule, we have to modify carbon's MS. So carbon's MS will not match with its position in the periodic table. Carbon's electron, the 6th electron, will actually be here where nitrogen is. So it will be +1/2. Okay? If you want to hear that over again, just go ahead and scroll back, rewind this, and then watch that again. Once again, even though carbon that has the 6th electron is positioned here, when you're working on the quantum number, you have to adjust the quantum number based on our understanding, the new information we got from Hund's rule that says the electrons fill like this first before they come back in pair. So that will adjust the electron. It won't change this electron for boron, but it will change the carbon electron. It will change, let's see, the 7th electron. The 6th and the 7th electron both get modified because now they have different positions. And then when you go back, you have this here, the 8th, the 9th, the 10th. So please notice the modified configuration for carbon. Okay, so just in case you're going online and seeing the resource, that's why we have to write this differently than what we're seeing here. Okay, now that I've explained that, we're going back here because these are all tied in together, right? We have our orbital diagram, so I'll call this orbital diagram. Now, the orbital diagram is not the orbital picture Please make sure when you're reading terminology or you're doing your work, do not skip over terminology, because the orbital itself is the one with the little bubbles and stuff, right? Without the word diagram. The diagram has the boxes, and then of course you have electronic configuration. Okay? So we talked about this last week, configuration, sorry, on Monday. I want to go ahead and work on more configurations. And then I want to talk about the orbital diagram that goes with the configuration. Okay, so remember the 4 quantum numbers for carbon without considering the Hund's rule. Once again, N, L, M sub L, M sub S. You all saw how I worked it out. The energy level is 2, L is 1, M sub S is -1, and then this is going to be positive 1/2, not -1/2. Okay, because this is what works with Hund's rule. Because of Hund's rule. Okay, so now that we've seen that this is a proper noun, now that we've seen that, let's go ahead and work these questions right here. Talks about write the electronic configuration for each element. So we're going to be working on these ones right here from scratch. I won't use this page. I'll just use the page to reference it. And then, of course, I'll give you the shorthand, right? So I'm trying to remind myself what I should talk about. We'll do the long periodic table, the shorthand, and then we'll do the orbital diagram. So we're working on magnesium first. For magnesium, I have a periodic table here. Find the atomic number or number of electrons. I have 12. So my configuration will be 1s, right? 1s, 2. Now, as I'm working on this, I keep thinking about different ideas. Let me bring the periodic table up here so y'all can see as I'm going through this, because some of you need that extra visual. So let me just copy this from here and bring it up. I thought I wouldn't need it until down here, but I was obviously wrong. Once again, it's okay to leave helium on the right. Just remember, though, helium is paired with the one on the left. There. Okay. I'm just going to copy this, bring it up so y'all can see what I'm referring to as I go through these sub-levels. Okay. So I'm working on magnesium. Back to magnesium. Mg. It has 12 electrons. So magnesium is right here, right? So I start with a 1s sublevel. The first and the second one are both in 1s sublevel. So 1s, I place 2. Then the next one is 2s, right? Since I have to place 12 electrons, 2s gets 2 out of my remaining electrons, the third and fourth electron. Then I go 2 to the right, and I see 2p. And 2p can house 6 electrons, right? 1, 2, 3, 4, 5, 6. Okay, so 2p, I put 6 electrons. When I check for my progress, so far I have 10 electrons total, right? I still have 2 more. And when you're working on the configuration, usually land on the element you're working on. So my last 2 will go on the 3s sublevel, and I place 2 there. Okay, so this is my regular electronic configuration. Since I worked on this on Monday, I want to work on it again today. The shorthand configuration. The shorthand configuration, remember that you have to have, so this is a quick review of the shorthand. You have to have the noble gas element, so right here, noble gas, or group 8. Noble gas or group 8 element, right? And the group 8 element takes care or represents the number of electrons we have in that group 8 element. And then the remainder configuration or remaining configuration. So you write the group 8 element in brackets and then finish up the remaining configuration. That makes it shorter. Now the group 8 element you select must be the highest, the element with the highest atomic number that does not exceed your atomic number, or the highest number of electrons does not exceed the number of electrons in your element. Magnesium has 12 electrons, right? So I look over here and I'm trying to figure out which group 8 element should I use. One that has the highest possible number of electrons, but not more than 12, right? So that will be, neon right here. Neon is my selected, my go-to group 8 element. So I'm going to write this in parentheses. My shorthand, bracket, neon. But when I write neon, I understand that I'm pretty much, it's a shorthand, right? Neon, the symbol by itself, represents 10 out of the 12 electrons. So neon right here is handling 10 electrons. I still have to show the configuration of the remaining 2. So that will be 3s2. And how do I know where to go next? You see where neon is? Just go to the next sublevel, and the remaining sublevel is 3s, and I place 2 electrons there. Okay. Now that I have this for neon, let me work on the orbital diagram. For the orbital diagram, it depends. Sometimes they want you to show so many sublevels. For many of them, they will just show you these. We haven't learned the term valence electron yet, but the electrons that are in the outermost shell, these are called valence electrons. I want to start using the terminology. So these are called the valence electrons. These are the electrons in the nosebleed section in the energy levels. These are electrons in the highest energy level. Please make sure, energy level. Please make sure you're actually learning the terminology as you're going through this part, because they'll keep using it. They might even modify it a little bit. It's very important for you to know what's being referred to. Okay, valence electrons are the outermost electrons in the sublevel or in the energy level, the nosebleed section electrons. Okay. So, for the most part, the orbital diagram is drawn for the valence electrons to make things easier for you. So for this one here, you can say magnesium has, of course, neon, like we just saw that. And then for the 3s2, once again, remember S sublevel only has one orbital, right? And we have 2 electrons here. So you can draw it just like that. That works too. Okay? So what I'm going to do is, just to make this go a little faster, I'm just going to stick with what they did here, because we do have an opportunity. We have a problem here where we get to draw out all the sublevels and draw the orbitals and the electrons in there. So I'll leave that for right here, because if I do it for all of these, it will take a longer time than I planned. Okay, so we're doing magnesium. What's next? We're working on phosphorus. So phosphorus is right here. Phosphorus has 15 electrons. So I'm going to work this out for phosphorus with 15 electrons. I don't want to go far because I'm trying to have this visual right here. So once again, even though I'm erasing it, feel free to rewind and then watch that. Phosphorus has 15 electrons. So how do we distribute the electrons? We start with 1s. All the first 2 electrons start with 1s. So at 1s sublevel, we place 2. That takes care of this and this, right? And then at 2s sublevel, we place the next 2. At the 2p sublevel, we place 1, 2, 3, 4, 5, 6. When I count my superscript, I'm now at 10, right? This is my checkpoint, 10 electrons. I keep going. At the 3s sublevel, we place 2. Then the 3p sublevel, we go as far as where phosphorus is. It takes us 3 boxes, right? 1, 2, 3. So 3p sublevel, I place 3. And so essentially these 3 right here is just the remaining electrons, right? So 10 plus 2 plus 3, yep, right here I have 15. Now, let's go ahead and write the shorthand for this. For my shorthand, phosphorus has 15. I have to go back and look at group 8. Let me see. Group 8 right here. Group 8, can I use argon? No, argon has 18. 18 is more than 15. I can't use argon. So I have to use neon. Neon again. Neon in brackets handles 10 electrons. And then that pretty much takes care of all of these, right? These electrons are represented by neon. Now I have to show the remaining. So I just copy these down here. 3s2, 3p3. Or if I don't want to copy it, I can just go here. From neon, you got to cover this part and then cover these three. Okay. Okay. What is next? What's next right here? Let's see. I did phosphorus. I did magnesium. These two are done. Now bromine. Bromine is all the way down here. So let me go ahead and erase these, the rest of these, and that will help me out. Okay, for bromine, and as the atoms get bigger and bigger and bigger and have more electrons, oh, you appreciate the shorthand, right? You appreciate the shorthand configuration. So bromine has 35 electrons, 35 bromine. Okay, so we'll keep going until we get to bromine. 1s, 2, right? 2s, 2, to the right. 2p, 6. Now we're here. 3s, 2, 3p. We go all the way to the end because bromine is down here. This is where we stop, right? 3p, 6, 4s, 2. Then we go to the right. 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. And then 4p. 1, 2, 3, 4, 5. 4p. 5. Woo! That was quite a journey, right? But we made it. We made it. Let me go ahead and erase these so I can see what I'm looking at right here. Okay, this is the full configuration. Now I'm going to write the shorthand. Bromine has 35 electrons. Bromine is right here, 35 electrons. So since it's 35, I can't use krypton as the shortcut or the shortened configuration, right? The shorthand configuration. But I can use argon. So Ar takes care of 18 electrons, right? So that takes care of, whoa, this is 10. It takes care of all of these. So all of these are taken care of by argon, right? If you don't feel comfortable looking here, that's okay. Write argon in brackets and then continue here. And this is 4s, right? So 4s2, continue here. This would be 3d10. And then, of course, all the way down here, 4p5. Okay, so hopefully you see how this goes. The full configuration, shorthand configuration. And then finally, aluminum, Al. Al has 13 electrons, right? So now I see why I try to write it. Okay, I have to write it a little smaller this time. So of course, 1 is 2, 1 is 2, 2 is 2, 2p6, 3s2, 3p1. Okay, shorthand for Al. Neon again. Neon makes it again. And neon handles 10 electrons, right? So neon takes care of these. So what we have left is 3s2, 3p1. Okay. Now that we're done with that part, we can move on. We have other configurations here. And I'm just going to talk about this. I won't go into the details. With the ones that have the transition metals like iron. With iron, you go through and they have pretty much 1s2, 2s2, 2p6, all of these in the shorthanded using argon. Remember, argon has what, 18 electrons? And so all of these are handled by the 18 electrons, and then of course you have 4s2, 3d6. Iodine, this goes to how many electrons? Iodine has 53 electrons. So for iodine, the shorthand has krypton, and of course the rest of the remaining sub-levels are shown right here. So just like what we did, they do the same thing over here. So feel free to look at that. Okay, so I wanted us to get to this problem here where we're writing the orbital diagram for sulfur and determine the number of unpaired electrons. So figure out the orbital diagram for sulfur and then figure out how many of the electrons do not have orbital mates. Okay, That's what they're asking. How many are unpaired? Which is hard to see when they're unpaired by looking at the configuration because it doesn't show them sorted out, right? So we're trying to see how this works out. Let me add a page here. Then we'll work this from scratch. We're working for sulfur, right? We're working on sulfur. Sulfur has how many electrons? I have my periodic table here, 16 electrons. So I'm not going to pull up the slide that has the periodic table. I'm just going to go by what I have here. This is going to be 1s2, 2s2, 2p6, 3s2, 3p6. Oops, no, we don't need all that because we're only going 16, right? Because from here, this is 10. So 3p4, okay? So from here to here, this is 10. From here to here, this is 6. So this is all we need, 3p4. Okay, so when it comes to the sublevels, they're showing us everything. Okay, so let me see if I can spread this out a little bit. The 1s and 2s, I think they'll be fine next to each other because I only need one box for each of these, 2s2. It's the 2p6 that I need more space for. And then 3s2 should be fine. And then the 3p4. The issue is the p's have more orbitals, so they need space. So I need one box for this, one box for that, and then one box for all the s's, right? 3 boxes for the p's. 1, 2, 3. Okay. Ooh, I got it. I'm never sure when I'm going to get them all in the same line. Okay. So the S's, we're following Hund's rule, Pauli's rule, and then Aufbau's rule. Aufbau was the one who said sort these out and arrange them according to increasing energy level. We did that. 1, 2, 2, 3, 3, right? It's 1 first, 2, 3, 3. Okay. Now we're filling the electrons in there. We're following Pauli's exclusion principle that says the electrons must have opposite spin. We're following Hund's rule when we get to these. These are Hund's rule right here. So up, down, that's Pauli's rule. Up, down, Pauli's rule. Then up, 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 that's Hund's rule that says make sure each sublevel has one electron first, then go back and pair it. Okay. And then we have up, down, right? Then up, up, up. These are 3. And this is the 4th electron. Man, I'm getting a lot of emails. I'll look at that later. It's hard to stay focused. Okay, I'll look at that later. Okay, this is it. So how many electrons do we have that do not have roommates? These ones here, these 2. 2 unpaired electrons. You have to see the orbital diagram to see the electrons that are unpaired. Does anybody have any questions? If you have questions, don't wait for me to ask. Just go ahead and type it. I tend to look up so I can see the messaging box just in case you have a question. I'll just go ahead and read it whenever I see it, okay? So this is it right here. Now they showed everything. We don't have to show everything. We could have just shown the valence. Because sometimes you don't have enough space and the element has too many electrons for you to show everything. Okay, so I kind of mentioned this before. When you look at the configuration, you have 2 major categories of electrons. You have core or inner electrons. These are the electrons in the lower energy level. They have better seats, so to say. And then you have the electrons with the highest energy level, the ones in the nosebleed sections. These have the highest principal energy shell, right? They're in the highest energy level. They are furthest away from the nucleus. These are called the valence electrons. The cheap seats, the discounted seats, okay? The ones close to the exit. So when you're looking at your configuration, you want to be able to identify which electrons are valence electrons. Looking at this right here, we're looking at silicon. Silicon has, is this silicon? They say silicon here, right? Silicon has got 14 electrons. So we got 10 and we got 4 right here, okay? So the 10 electrons are the core electrons. Then we have the remaining 4 as the valence electrons. So what they haven't mentioned here that they will mention later on is the number of valence electrons are equal to the group number of the element. Okay? Caveat, this rule works for group A. Remember, group B's are unpredictable, right? So number of valence electrons equal to the group number. So I'll say here 4 A elements. Remember, the A elements are the S and the P. This was 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. Right. The S and the P elements tend to be more predictable, so we can go ahead and predict their behavior easily. And they tend to be more trendy. The D block, these are the B's. The B's. The D and the F are the B block elements. These tend to be unpredictable because they are a little bit more complicated. They're able to do a lot of different things that makes it more difficult for us to predict their behavior. While these here have fixed charges, we'll learn that later on. We haven't gone to that part yet. I'm trying not to get ahead too fast. I think I touched this. I didn't mean to. Okay, there. Okay, so valence electrons, once you write out your configuration, find the ones that have the highest energy level, right? Because we did write this according to Aufbau. Aufbau is a scientist that says sort out your sub-level and increasing energy level. So before I continue real quick, Aufbau, so that you guys do not overlook this, talks about arranging sub-levels and increasing energy. Even though there are exceptions to his rule, that's his general rule, right? In other words, 1s first before 2s, because 2s has higher energy level, etc. Pauli, I'm trying to paraphrase the rule. Pauli says that 2 electrons can occupy an orbital if they have opposite spins. Okay, so as we're working on this, behind the scenes, we are following these rules. And we just learned about Hund today. Hund's rule says in degenerate orbitals, place 1 electron in each orbital before pairing. Okay, we are following these rules, but we can't just follow them. We need to know them, because I think it's been a while since I've looked at your homework. I'm working on my 1412 class right now. I think there are questions that they ask you, which of these pictures, they give you an orbital diagram, is not following Aufbau's rule. Well, if you've forgotten Aufbau's rule, how do you answer that? You review it, of course, right? But Aufbau is all about arranging the sublevel in order of increasing energy level. Remember, I told you guys before, the periodic table, if you go from left to right, from left to right shows you the sublevel in the order he was talking about. Okay, and then Pauli is the one that shows us how we can have 2 electrons in one orbital in the correct way: up spin, down spin. Hund is the one that says when you have many sublevels like these, you have to make sure each one is singly occupied before you go through and pair it. Okay, so just a quick recap. Once again, feel free to rewind and watch that part. Oh, okay, so this problem here is saying write electronic configuration for germanium, Ge. Identify valence electrons in the core electrons. Okay, once again, new page for that. Germanium, let me find it right here. Ge, number of electrons, 32. Okay, so 1s2, 2s2, 2p6. Now I'm looking at a periodic table as I go through this. 3s2, 3p6. Now I'm on argon, right? This is 10 electrons here. I'm at 18 electrons. I keep going. 4s2. This is at 20 electrons. 3d10. I'm now at 30 electrons. And you can tell 3d10 is at zinc, so 30 electrons. Now I'm at germanium, 4p2. 4p2 puts me at 32. Okay, and you can count 2 plus 2 plus 6, 10. 2 plus 6, oh, plus 2, 12, plus 6, 18, right? Plus 2, 20, plus 10, 30, plus 2, 32. Okay, so the superscript should add up to 32. Okay, where was I? Oh, they said, this is my configuration. Find valence electrons. My valence electrons come from 4s2 and 4p2. How do I know that? I'm looking at all the energy levels, the numbers before the letters, and these are my highest. So when I take the superscript part, this part here, and add those up, my total is 4 electrons, right? And then what else they asked for? They wanted core electrons. They wanted core electrons. So the remainder of these, let me use a different color, orange. These right here, these end up being our core electrons. So all the other ones that didn't make the cut, these are all our core electrons. So our core electrons, the ones I highlighted, and what do we have there? We're going to have all the way to here, 18 plus 10, 28. So core electrons, we actually have 28 electrons. All the remaining, right? 28. Yeah. So hopefully you see that. Now the one thing they haven't added, they haven't asked, but I feel like we should add here is group number for germanium, Ge. Group 4. When you look at germanium, it's in group 4a. Remember I told you guys the group number matches with the valence electrons? There. Okay. Germanium is in group 4a. I think I can find it right here. Yeah, right here. Group 4a. So everything in group 4 should theoretically have 4 valence electrons. And then this one here in group 3 should have 3 valence electrons. So hopefully you see that, right? So let's start with the beginning. 1A will have, so 1A, 1 valence electron. And then 2A, 2 valence electrons. 3A, 3 valence electrons. 4A, 4 valence electrons. And so on. So this continues all the way to group 8, where everyone except for helium have 8 valence electrons. So right here, group 8A, all elements except for helium have 8 valence electron. Remember, helium, when it comes to electrons, behaves like its cousins back here. Helium actually has 2 electrons like its group right here, but it is placed here because of its behavior, not because of the number of electrons. Okay. Yeah, so helium will have 2, the remainder will have 8 electrons, just in case you're wondering. Okay, where do I go now? Oh yeah, so they illustrate that here, right? They show you the valence electron. One is 1, 2s1, 3s1, all the way here. I told you all this group B is complicated, right? This one here ends with 3d10, 4d10, 5d10, kind of predictable. But then we come here to some of these, and you have 4s1, 3d5, 5s1, 4d5, 6s2, 5d4. What's up with that? It's complicated with this group. They're not predictable. So we don't group, that's why we group them as B, as in it's complicated. These ones here, there's more predictability. 2s2, 2p1, 3s2, 3p1, 4s2, 4p1, 5s2, 5p1. You see the trend, right? And then, like I told you guys here, helium behaves more like group 2 as far as the configuration is concerned, but behavior is more like its family. And you can see the configuration right here. So when you add the superscript on these valence electrons, it should add to the group number. So see right here, for fluorine, 2 plus 5 equals 7. And that's true for all the elements in group 7. So I'm going to continue from here. Feel free to look at the rest at your own time. Okay. So here they're talking about orbital blocks and their position in the periodic table. You can write electronic configuration in the periodic table, refer to the periodic table, and write the configuration, electronic configuration for selenium. So based on where selenium is, I think we've been kind of been doing this whole time, but they want you to write the periodic table for selenium based on the shorthand configuration using the periodic table. So of course, selenium right here, they don't show number of electrons, it's 34 electrons. Yeah. So argon will be the one you put in here, takes care of 18 electrons. And then from there on, from argon, we have 4s2, 3d10, 4p4. And that's how we get this right here. We've been doing that this whole time. Okay. Now that we've looked at the generic group, group A, we're now moving on to the complicated group, group B. Transition and intertransition metals. This is the D and F block elements, also known as B elements, right? There's so many names. Transition metals, the D block elements, and intertransition metals, F block elements, exhibit trend differing from those in the main group elements, referring to the group A, the S and the P block. The 4s is lower in energy than the 3d sublevel. I already discussed this before, right? That was due to penetration. Due to penetration. So if you didn't see this, go ahead and watch the previous video. I feel like I have a YouTube channel. Anyway, this is a Blackboard channel that nobody really cares about. Yeah, the 4s fills first before the 3d because the 4s is able to penetrate and get ahead of the 3d slightly, but so that it is able to fill first. Oh, okay. Hold on a second. It should be, what chapter is this? This is 3, right? Yeah, it should be in collaborate. Now I have these old ones right here, posted right here. So when I get done with these ones, because I already have some posted right here if you want to work ahead, when I post the new ones, so I don't confuse the new ones with the old ones, I put a date on the new ones. Okay? So I see I haven't posted the other ones here. I'll put a date on the new ones. But yeah, they're all here under the collaborate. So when you go to your, let's see, course assignments here. Oh, my bad. Let me look at the student view because you're all seeing too much. Right. When you guys go here, course assignment, it's chapter 3. And then they're all under the folder collaborate. Okay. So yeah, hopefully that helps. And then you can work ahead too, because I have those are from my previous semester. For those of you who are wanting to work ahead, so you can work ahead, because I have a recording. Of course, I don't have a script, so every semester's recording is very different, right? I'm not going by a script. I just go with the flow of the class. Okay, so right here we're told that these have irregular electronic configuration. They're not very predictable for that reason. Yeah, we work with these. And there's some cases where you cannot use the method we've been using so far to figure out the configuration. Okay, we're told that some metals have irregular electronic configurations. in which the S sublevel, that's what this is, whatever energy level it is, only partially fills before the D sublevel, or doesn't fill at, I think they meant to say at all, at A, at all, right? An example of that is chromium, molybdenum, copper, and silver. What they're trying to say is the d orbital elements are so unique that it's not easy to use the method we've been using so far, the periodic table method of just kind of counting from left to right to figure out what the configuration is. So the example for those elements, chromium, molybdenum, copper, silver, I'll say here platinum and palladium. So, well, if we can't use the periodic table to find the configuration, what do? We're told here, therefore, their configuration, these, must be found experimentally. Well, y'all can't go do an experiment, right, to find them out. So what do? You actually, in this case, you will find the configuration online. Okay. Now they have these right here. So in your lab, the lab that goes with this section here, you're supposed to do a configuration. When it comes to platinum, don't use the periodic table. You'll get the answer wrong because that method falls apart. For these, you have to use a reliable, either your textbook or a reliable internet source. Okay? This is saying expected. This is if you use periodic table. Now, the periodic table method works for many of the elements, right? It does. It works for many of the other elements. But when it comes to these ones, because these elements behave differently than expected, their configuration cannot be predicted, and therefore you cannot use the periodic table. This is what scientists thought the configurations were after they used the periodic table. Then they ended up being wrong. And then they had to find it out experimentally. Experimentally, they realized the way chromium behaves in experiment is consistent with chromium having this configuration versus that. Copper, this configuration versus that. So remember that when I was a student, I'm just going to tell you my feelings. I used to get frustrated, like, why can't we just learn the truth? And I had a student ask me the same thing, and I'm like, you know what? I understand what you're saying. Why can't we just learn this versus learning this before we learn that, right? Because that's, for me as a student, I was like, that's one more thing I have to learn. But chemistry is a problem-solving class. That is the emphasis. You're learning information, yeah, but you're learning problem-solving technique. So we're trying to see here how they solved this problem. This was a problem because the method they had was giving them the wrong answer. What they do, they did an experiment. So now we have the correct information, but now we also know how they solved the problem. So when we run into this situation in our future, if this becomes our career, or we have to know this, we will know how to solve the same problem because we have gone through this material. Okay? Just in case. So yeah. Now, some of these experimental results kind of make sense, some of them don't. So I'm going to go through and show you the ones that sort of make sense. Okay. Wait, where's the page at? It's important to click the right slide. Okay. So I'm looking at chromium here. Now, scientists, for chromium, we're going to be looking at what looks like just the valence, right? Because they have AR up here. Chromium has 24 electrons, and we are only showing 4s and then 3d. Okay, scientists expected chromium. Remember 4s, you have, for the s level, sublevel, you have one block, right? One orbital. For the d, we have 5. 1, 2, 3, 4, 5. Okay. It's so hard for me to draw these boxes. Anyway, we got 5. So argon takes care of 18 electrons. We have 6 left over, right? Based on the rule we've seen so far, we're thinking, okay, up, down. This takes care of 2. So we have 4 left, and then we have 3d4. That's what they thought, right? So this would be up, 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 up. 4. Well, the way chromium was behaving in experimental problems wasn't like this, like it had this configuration. It was behaving like it had this configuration here. Ooh, okay, I erased more than I meant to. It was behaving like it had this configuration. So they had to come back here and adjust 4s1, 3d5. Now, how do you explain a preference? Now, remember, we are studying elements, right, who do not communicate verbally. Elements don't tell us, this is my preference and this is the reason why. So we are trying to, in our own understanding, understand why, right? We're doing experiment, we're thinking, we hypothesize, we're thinking, right, based on experiments, that this is why the elements wants to do it. And then we go that with that thought. Unless somebody else challenges our thought, we just proceed with that thought. And it keeps getting tested over and over again, and it graduates from hypotheses to theory. It takes a lot to get to a theory, right? It has to be tested over and over and over again before it eventually graduates to theory, where everybody now obeys it like a rule. Anyway, so scientists are thinking, well, we think the reason why chromium likes this is because of other results they saw. Scientists noticed that elements have a preference. Elements in general prefer half filled or full. This is not like fulfilled, like, fully filled, fully filled, fully filled sublevels. Okay, so this is their preference. Like if you were to interview an element, they'll tell you this is our preference according to us. Okay, well, how do we know this is what they like? Because when they achieve the state, they are very stable. But half filled is not the same as full filled, right? So full filled orbitals are more stable than half filled. So even though both of these are preferred, right? Full filled and half filled are preferred, even in the preferential state, there is a higher state. So yeah, if the electron has a choice, or if the element has a choice, it will go with half filled. But if possible, it will rather go with full filled. So full filled tends to be a lower energy. Half filled tends to be relatively low, but slightly higher than full filled. So the way that chemists interpret the communication from elements is stability. If an element likes something, it is stable. If it doesn't like something, it becomes unstable. Okay. When I was learning this, I was trying to really, really embrace this concept, which I couldn't embrace as a student. I mean, I shouldn't say couldn't, I just wasn't. So I was thinking, when kids are content, they're very calm. When they're not content, they're very restless, right? So what if the elements are behaving like that? So contentment goes with stability and calm. And then lack of contentment is unstable. Okay? Yeah. So chromium prefers to be in a more content state. So it takes the electron from here, which is the gap between these two is not that much. Remember they said it back there? The energy gap between these two is not that much. It does cost the electron some, but not that much energy to take the electron from here, put it here, and now it's stable. It is more happy in this state. Okay? So that explains that. This one here, you can see the same thing. I won't draw the whole picture. Copper took the one electron from here to put it over here. So this one is 10. This is fully filled orbital. You can see that, right? Fully filled. This is half filled. Half filled. Oh, I can't spell today. There. This one here, you can see that molybdenum. You can see, okay, wanted to be half filled. Took one electron from here to put it here, I guess. Half filled. Now, what is up with that? We don't know. This one here is not explained. Ruthenium is doing what ruthenium wants to do. It is what it is, okay? Because this is neither have filled nor filled. Now, it couldn't take its one electron and give it to that because there is no more room here in the s orbitals. Like, excuse me, capacity is filled. No, don't bring your one electron here. So we don't know what's up with that. This is not explained. This one here is like, come on, really? You gotta get fulfilled that bad? You didn't even leave the s orbital, the 5s1 electron. No, it took both. Palladium is serious about this. It took both electrons, put it in here to become fulfilled. Now, why some elements are able to do that and others aren't? The ones that are able to do this are transition elements, those strange ones. Okay? Do whatever it takes to get stability. Now, when they're about to react, they kind of behave differently. I'm telling you, these elements, they're interesting ones. But in the periodic table, you want to know some categories of elements because we tend to refer to them a lot. Noble gas elements, these are group A. We tend to refer to them a lot when it comes to, how should I say, the picture of stability. Okay? So they're called noble gas because back in the days, most of the scientists that came up with this, they're Europeans, where in Europe you have kings and queens, and they're usually noble, right? Noble people, nobility. So everybody looks up to the queens and kings and princesses and princes, and everybody wants to be like them, and they only dream to be like them. So they call these noble gas, not because they've done anything good, okay? Kind of like royalty, okay? The other term for these gases are inert gases. The rest of us, we call them inert. I mean, we call them noble gases too, but inert. What makes them noble gas? Why do they get a name for themselves? Because these tend to be like all, I shouldn't say all, but most of the other elements either gain electrons, lose electrons, or share electrons because they want to be like noble gases. So other elements desire to be like noble gases. Once again, when we say desire, want to, these are human attributes, right, that we're ascribing to the elements. It's not like they interview the element and said, I really, when I grow up, I want to be like Krypton. It wasn't anything like that. How do we know the desire is there? When they become stable. They do a lot of changes, undergo a lot of transformations, and then when they're stable, scientists were noticing when the elements were stable, it's when they had these kind of configurations. So they're like, oh, maybe they want to be like these elements. you know so how do the other elements achieve that? We'll see later on that group A elements are the ones they lose, they gain, or share electrons, and they have a goal to become like noble gas elements. Okay. When I was reading this, I was like, okay, when we were kids, we're told, be yourself, just be happy with yourself. And these are elements, they're not people, but look at them. They're trying to lose, gain, or share electrons. They have goals too, to be like the noble gas elements. So they're not people. This is our interpretation of what they're doing. So we just go with that. Okay, so we'll see an ongoing behavior later on as they try to become like the inert gases. We talk about alkaline earth metals. These are group 2, and then alkali earth metals, group 1. So you want to be aware of these terms right here. Some of them are used in batteries, alkaline batteries. Halogens, group 7. These are discussed a lot. Fluorine, chlorine, bromine, you've heard of them. They're discussed a lot. So you want to be aware of these terms because when they refer to halogens, they mean something, an element in group 7. Alkaline earth metals in group 2, alkali earth metal in group 1. So I don't see that here. Okay, so alkali group 1. Okay. Okay. Yeah, so talking about this element here, this group here, group 8, they have a full shell, or they have full sublevels, or you can say energy levels. They get the special name because they're practically inert. Inert means they don't want to react. Okay. So when I was learning this, me and my friends, I was really, once again, was trying to bring this into my life. So I'm telling my friends, oh my goodness, it's so like what is it called, uppity. They don't want to mix with the regular elements and everything. They're so non-reactive. They're too good for that kind of life. They're practically inert. It's very difficult to get these elements right here to react. Now scientists, you gotta, if you're a scientist, you gotta be one of those people who is not satisfied with no, right? Scientists are like, no, we're gonna find a way to make these react. Do they have compounds with xenon and all the other stuff? Yeah, they do. Did they force the elements against their natural will to react? Yes, they did. And were they able to do it? Yes. So they can say they could do it, right? Did it cost them a lot of time and energy? Yes, it did. Was it worth it? I don't know. But they use them for research. So in a way, yes, they are. Okay. Because they're like, yeah, they're non-reactive practically. They're inert, don't want to react because they're stable and they're happy. But scientists are like, no, we're going to mess with that. And we're going to go in there and force them to react. So they do manage to get them to react, and they use the products for research. And their findings, right? They publish. Yeah, the alkali metals, these are in group 1. So you want to be aware of the alkali metals. These metals lose 1 electron, resulting in, as it says right here, so alkali metals, let me see, there should be a table here that shows you the group numbers. We're kind of getting there. But alkali metals, these are group 1. So group 1 metals tend to lose electrons. So this is kind of like an overview as we get into the other sections, right? They lose electrons. When they lose electrons, they form a charge of +1. So we're told here group 1 loses 1 electron. Okay, so let me kind of give you guys a summary. We haven't gotten to that yet, and I wish, because I have a thought, I'd rather just complete the thought. As far as you guys' level is concerned, and as far as what we're going to be covering, the maximum electrons that can be lost, maximum electrons to be lost is 3. Okay, so an element, I'll say here number of electrons lost and then charge. An element can lose 1 electron. I should say here 1 electron. I should write this differently. I'll give an example. For example, hydrogen. Hydrogen is in group 1. I'll add here group number. I'm literally making this up, so excuse me. Group number. Group 1 element, example hydrogen, loses 1 electron, and it has a charge of +1 because it lost 1 electron. Okay, the charge here is reflecting, not you can look at it as reflecting the charge loss, but it's truly really reflecting what remains, like what we're seeing, what is remaining, not what left. Okay, and we're seeing an imbalance of charge. So what I want to show you guys on the side here is how we get the +1, because it was a trip with one person. Hydrogen has 1 electron and hydrogen has 1 proton. Hydrogen actually doesn't have a neutron. It's intriguing like that. But it has 1 electron and it has 1 proton. Okay? So then we see the transformation, lose 1 electron. And we're left with what? 1 proton. 1 proton. Because the electron is gone. I guess I'll show it right here to separate now. The electron is by itself. Okay? So since the hydrogen element remains, but it now has a charge of positive, this ion that's formed is called hydrogen ion, and it actually also has the name proton. Why? Because that's the only subatomic particle remaining in hydrogen. So it has the name hydrogen ion, aka proton. It's kind of like you're called your name and somebody probably calls you daughter or a son or a pet name. Okay, so hydrogen is called hydrogen ion or a proton. Okay, so this is hydrogen ion, aka proton. Group 2, I'll pick one from group 2. Magnesium, Mg. Mg loses 2 electrons and it becomes Mg2 plus, right? Because the number of protons and electrons were even, but after losing 2 electrons, now you have 2 extra protons without matching electrons. So the electrons are gone and they're not there to neutralize the protons, right? Number 3, I'll go with aluminum, popular one. Loses 3 electrons. So group 1A, 2A, 3A. 3 electrons becomes Al3 plus. Okay? So this is the normal trend we're used to. Group 1 forms a charge of +1. Group 2 forms a charge of +2. Group 3 forms a charge of +3. When I say 1, 2, 3, I mean 1A, 2A, 3A, because the other ones are not predictable. They're complicated, right? Okay. Now I'm going to do the opposite part and show you the reverse, which is the ones that are gaining electrons. So for ones that are gaining electrons, I'll go with the opposite group, which is 5, 6, 7. Group 5A, group 6A, group 7A. So with this one here, I'll go with 5A is nitrogen, 6A is oxygen, 7A is fluorine. This one gains 3. This one here gains 2. This one here gains 1. The difference here is the number of electrons that are being gained allow the element to actually have a configuration like the noble gas configuration. So in the end here, nitrogen now has 3 extra electrons, but without the proton. Oxygen has 2 extra electrons without proton. Fluorine has 1 extra electron without protons. So we talked about this right now. I'm going to go ahead and move on. Make sure you know alkali metals, alkaline earth metals. I won't go over that in detail because you can just read over that. I've discussed the charges here. What I want to talk about is, I want to talk about the configuration of the D block elements because these are complicated, okay? Metal elements make up the majority of the elements in the periodic table. They are located in the D block area, the transition and intertransition metals. They're in the D block for transition. Intertransition is F. Transition is D of the periodic table. In chemical reaction, metals will lose electrons from S. Actually, this is referring to transition metals, right? These ones right here. Oh, I want the brighter yellow. This is not bright enough. I want it bright. Transition and intertransition metals lose electrons from S first, then D orbitals to form cations. They're complicated like that. The other one had the principle, last one in, first one out. Not transition and intertransition. They're different. They lose from S first, then they lose from D. When it comes to losing electrons, it's like, okay, the one that has the highest energy level is the one that loses electrons first. So after discussing that, I want us to now go, I'll skip over this part here because this is just showing you metals, non-metals. I'll come back to that. There should be a question here that relates to that. Isn't there a question here that relates to that? No, there isn't one. Snap. There is one all the way down here with iron. Okay, you know what? Let me use titanium, okay? Let me give you guys my own example. Oh, the way they write these PowerPoints. Okay, so while we're here, I want to add an example to this to illustrate what's happening. Let's write the configuration for titanium. Titanium has 22 electrons, right? I'm going to write the shorthand because I'm just here to make a point. Ar has 18 electrons. After 18, let's see, potassium and calcium make 4s2, and then titanium is 3d2, like that. Okay? Yeah, this makes 22. So let's see. Let's say we're trying to make titanium lose 2 electrons. That's what this is saying, right? Titanium loses 2 electrons. So if it loses 2 electrons, it doesn't have 22 anymore. Now it just has 20. How do you write the configuration for that? Remember, it says right here, take electrons from S first, then D. So D block and F block elements lose electrons from S sublevel first. Okay, so I leave the AR untouched. I have to go to the outer energy level. Normally you take it from here, right? But because this is transition, take it from here. So those 2 electrons, they're gone. If you want, you can write 4s0, or you can just leave it completely, and then 3d2. You can write it this way, or you can say it's argon 3d2 with the 4s completely gone. Okay, because they said remove electrons from the S sublevel first before you touch the D. Now, had they said you're removing, okay, excuse me, had they said you're removing 3 electrons, say for example they said Ti3 plus, and you only had 19 electrons left, then you go with Ar. Of course, the 4s is gone, then 3d1. You don't have a choice then. You have to go and take it from the D. Or you'll be left with Ar3d1, like that. Okay? You only go after the D when the 4s is emptied out. That's what they meant by that. Okay? So now I'll go back to this real quick. Here they're showing you metals, metalloids, and nonmetals. The zigzag line here separates the metals from the nonmetals. The nonmetals are in this aqua pink, not pink. Oh my goodness, I was wrong. Aqua tealish color, right? And that's nonmetal. The metals are the majority. These are beige, army green. I don't know that color, whatever that color is. And then on the border of the 2 groups, you have elements that have the behavior of both, and these are called the metalloids, the ones in purple, metalloids. Now, the most important, I shouldn't say most important, the most popular metalloid is silicon, right? Now, back in the days when I asked, what do we know silicon for? It was like semiconductors. And I'm like, yeah. These days when I ask that question, I don't know if I want to even ask that question, right? Yeah, the reason why silicon is popular in the industry is because it's used to make semiconductors, which we get to enjoy in our phone. And I really love my phone, so I really love the idea that silicon is out there helping us to make the phone that we have currently possible, right? It's used in phones, computers, electronics, and all other things. I do love my electronics, right? So metalloids are called metalloids because they do have both metallic and non-metallic characters. So it shows that right there. We'll talk about non-metal behaviors. These actually gain electrons, right? And they form anions. We saw that before. Anions are negative ions. Okay. So we talked about halogens here forming -1 charge. I already discussed the main points of this. Go ahead and read the rest of these as you're working on this. Now we're going to electronic configuration and ion formation. So I kind of mentioned this before. Now we're going into it in details. So we're told that ion formation can be predicted by an element's location in the periodic table, referring to the A ones, right? The group A. These atoms form ions that will result in an electronic configuration that is the same as that of the nearest noble gas. Metals form cations, positively charged. Remember, +1, +2, or +3. And then nonmetals form anions, negatively charged. This is -1, -2, -3. Okay, it all goes with where they're located in the periodic table. Group 1 form +1, group 2 form +2, group 3 form +3. Transition and intertransition metals, these tend to form many charges, so we don't learn them holistically. We kind of learn them by themselves. We just memorize them because they tend to form many different charges that are not very predictable. Okay. And then we're told here halogens tend to form a charge of -1. So we're now seeing the charges based on the group position. There's a typo here. Sorry, I can't change it. So all I do is mention it when I get here because I didn't draw the picture. I can't redraw the picture. So group 1, of course, forms plus 1, right? So this is group 2 forms plus 2, 2, 2, 2. Skip over the D block. Group 3 forms plus 3. Group 4, because it can't lose or gain 4 electrons, then it's just you skip over that part. Group 5 gains 3 electrons to 4 minus 3. Group 6 minus 2. Group 7 minus 1. So I already talked about this before, right? So we're told here, predict the charges of the monoatomic single atom ion formed by these main group elements based on their position, right? That part is implied. Aluminum and sulfur. So aluminum is right here, right? So the charge will be plus 3. Sulfur is right here, so the charge will be minus 2. Okay? They go on explain the configuration and all that stuff. We're not doing all that stuff right now. We're just looking at the charges. But since they're showing this for aluminum, when aluminum does lose its 3 electrons, let me show you right here. When I was learning this in school, because we started when we're kind of younger, I saw it as a game, right? When aluminum loses 3 electrons, it now has 10 electrons. So it moves back 3 spaces. The element here is neon. Here we have argon. Here we have krypton. Here we have xenon. Right. So before aluminum loses 3 electrons, it has 13 electrons, right? When it loses 3, it moves back 3 spaces. So it goes from here to here to here to where neon is. So after losing it 3 electrons, aluminum has the behavior of neon. After gaining 2 electrons, sulfur has the behavior of argon, or the configuration of argon. How do we see that? Look at where sulfur is originally. Add 2 electrons. 1, 2. Now it has the behavior of argon. Not necessarily the full behavior, but it has the stability of argon. While it has lost 2 electrons. I'm sorry, it has gained 2 electrons, right? Bromine gains 1 electron to have configuration like krypton. Iodine gains 1 electron. So as we see this here, let's see. I will talk about periodic trends next week. How are we doing? I think you guys have your common ion exam coming in next, right? So we'll talk about this part here. For the common ion exam, what I would say, since I don't get to talk about that before we get to it, let me look at this right here. Because that's what's listed next here. Okay. So for your common ion exam, you want to go over chapter 4. Chapter 4 is where we have all those ions and stuff listed, right? The names of the ions. So go over chapter 4, even though we haven't discussed this yet. As far as the naming is concerned. Oops, that's the wrong PowerPoint slide. Chapter 4, I think, has names, if I'm correct. Yes, it has a naming system here. So to prepare for the exam, go over this, learn how to name the compounds and the ions. And that way, when I'm going through it next week, we'll go over this faster. Okay? And actually, here's the thing. Because we're kind of falling behind and I want us to get into this here, I'm going to be shooting a video for 1411 to finish up the chapter. Okay? You're free to work ahead because I do have pre-recorded videos. So I want to go ahead and finish this chapter here because I'm trying to make up for the week that we missed. And so I'm going to be finishing the remaining of this chapter. Let me write myself a note to say where to start. Start here. This afternoon, I'm making up a session for my other class. For you guys, my goal is to work on this on Friday. So Friday, I won't do it in the morning. The morning is kind of early. So Friday, I will be working on this, I'm thinking around 2 p.m. Okay? So I'm writing myself a note, 2 p.m. Friday. I will send a reminder if you guys are able to join. Okay? If you're able to join, great. If you're not able to join, that's fine. It's just that I want to make sure we're not falling behind too much. okay? Because I feel like we're already falling behind, and then we're falling behind even further. So I want to make sure that next week we can start with chapter 4 to give you guys a chance to at least go over the rules of nomenclature, okay? So go over the rules, learn how to name this, because when I go over this in lecture, I don't necessarily go over the rules of naming elements and ions. I just go over the rules of naming compounds. So make sure by next week you have covered the ions and the elements, okay? So if you guys are able to make it on, will you guys be able to make it on Friday? Anyone? Around 2? Or is there a better time? Okay. So I will send a reminder like I did today to the class to say, hey, I'm about to shoot this video. So if you guys can join, please join. Okay, that works. I will see you guys on Friday at 2. Have a nice day.